Okay, we are ready for lesson 15 of module 2, an informal proof of the Pythagorean theorem. This lesson can be done before or after the end of module 2 assessment because there are no questions on the assessment regarding the Pythagorean theorem. We are going to be doing lessons throughout the year on the Pythagorean theorem. There will be one in module 3 also, but we won't attack the Pythagorean theorem in depth until the end of the year. I think it's in module 7. So right now these are just sort of preview lessons, but they go along with what we're learning about geometry in module 2. So that's why we're doing it now. And we'll just continue to revisit it. It's one of the really important ideas in math, the Pythagorean theorem, and so it's good to have multiple exposures to it. Okay, so let's dig in and look at lesson 15. Okay, so the Pythagorean theorem is based on right triangles, and so I've drawn one here, and here is the right triangle in my diagram. Here's the right angle of this right triangle. So let's label our triangle A, B, C by the vertices. And what we're going to do is also label the sides, because the Pythagorean theorem deals with the side lengths. So the side opposite angle C, right here, we're going to call side C. And the side opposite angle B, we're going to call side B. And then the side opposite angle A, we're going to call side A. So side A and B are also called, have a name, they are called legs. So side A is a leg, side B is a leg, and those sides are next to the right angle. So the sides next to the right angle are the legs, and then the side opposite the right angle is called, has a different name, it's called the hypotenuse. The hypotenuse, I always spell it wrong, yeah, that's right, hypotenuse. Okay, and that is something to notice about these right triangles too is I've got two other angles, and because this angle here is 90 degrees, these other two angles have to add up to 90 degrees. If I take the sum of this angle and this angle, they're going to be 90 degrees as well, their sum. So notice that angle C being 90 degrees is the largest angle in the triangle, and that means that this side C, the hypotenuse, has to be the longest side in the triangle too. The hypotenuse can't be shorter than either of the legs, and that has to do with the amount that this angle opens up, okay? So the smallest angle, which looks in ours to be angle B. Angle B is the smallest angle, so leg B is going to be the shortest side in that, in that triangle. And that's kind of intuitive why that's true, but so anyway, so there is our right triangle. So what the Pythagorean theorem tells us is it gives us a way to determine side lengths in a right triangle, and it gives us a relationship that if I take, and let me get myself some room here. If I take the legs, the side lengths of the legs, and square them and add them, it adds up to the hypotenuse. So what that looks like in an equation form is that, I'll get my pen back here, let's pick a different color, is that A squared, or A times A, plus B squared, the sum of those is equal to the hypotenuse squared. So A squared plus B squared equals C squared. What that means is that if I know any two sides, it doesn't matter which two, I can find the third by writing an equation and solving it. All right, so we are going to work through a proof of the Pythagorean theorem, and you can take some notes in a blank area of your notes pages for this. Some of the geometry facts that we're going to use are things that we talked about in this module. The first one is that corresponding side lengths and angle measures in congruent triangles are congruent. So if I have two triangles that are congruent, the side lengths are going to be the same measure, the angles are going to be the same measure. And we know that from the rigid motions, right? We can map it right onto congruent triangles can be mapped onto one another. All right, the triangle sum theorem, that all the interior angles of a triangle add up to 180 degrees. We've used that extensively in this module. And also something about when triangles are congruent, their side lengths are congruent, they're going to have equal areas. Okay, so you can think about that, but it pretty much follows from the fact that the side lengths are equal. Okay, so let's look at this. Okay, so I've got a kind of fancy drawing for you here. What we've done is taken 4 copies of a right angle. So here is, let me get my pen. Here's one of them here. So this is our right triangle, sorry. So each of these are 90-degree angles. Okay, so what we've created is by making, 4 copies of this triangle. Here's 1, 2, 3, 4 copies of the triangle and arranging them to form a large square. Okay, and notice the side lengths of this square. Right here. The side lengths of this square are A plus B. A plus B. So it's a square, A plus B square. And it looks like it's forming a square here in the middle, but we're going to have to do a little bit of work to know for sure that that is a square. We know that the large one is a square with side lengths A plus B. If this is a square, it's going to have side length C there in the middle. Okay, so let's look at that. Let me clean that up again. Okay, so remember, we're trying to show this. We're trying to show that if we take A and square it and then add it to B squared, we get C squared. So I'm not expecting you to be able to recreate this proof, but I want you to be able to follow the proof. So that's our goal here today. So what I'm going to do now is I want to find the area of this large square with sides A plus B. All right, so I'm going to get a blank paper for me here. So the side lengths are A plus B. And so I've got this square over here. And so the area of that square is going to be the side times the side, right? So the area here is A plus B squared. Okay, so see if you can do that multiplication using the distributive property. You can pause the video and see if you can do that on your own. We did that back in module 1 on one of the lessons, but you might not quite know how to do that, and so I will work it out for you. But if you want to do it on your own, you can pause right now. Okay, so what I want to do is I want to multiply these two quantities together, and I want it to be for any A and B, so I can't add them first. I would normally add what's in the parentheses and then multiply, but we can't do that because we're using variables here. So what I'm going to do is I'm going to use the distributive property, and let me get a different color here so we can see what's going on. I'm going to take A plus B, what's out in front here, this amount here, and I'm going to multiply it by each of these things separately and then add them together. So I'm using the distributive property. So I'll have a plus b times a, that's the first one, plus a plus b times b. I have to multiply them separately. So we're going to use the distributive property again. I'm going to multiply a times everything in there and b times what's in the parentheses. So I'm going to have a squared, a times a, plus a times b, and then that will be the first one. And now let's do this one. And this one I have b times a plus b times b, which is just b squared. All right, so if I straighten that out, I have a squared. Now let's look carefully at these two terms in the middle. I have AB and BA. Notice those are really the same thing. I could rewrite this BA as A times B, because B times A and A times B are the same number. They're the same quantity. So I have an A times B and another A times B. So I can rewrite that. I'll just keep my purple. I can rewrite that as 2 times A times B, right? Because I have two of those, so it's 2 times A times B. Would simplify that. And then I have still my plus b squared. So this expression right here, a squared plus 2 times a times b plus b squared, is the area of that large square in our diagram. All right, so remember that. Okay, so now we know the area of this large square with side length a plus b. Now I want to look at the area of one of these triangles, because what we're going to try to do is subtract. We're going to take the area of the whole square, subtract off the triangles, and that will give us the area of this region left in the middle here, this part. Okay? So that's our goal. So what is the area of one of these triangles? Well, if you remember, the area of a triangle is 1/2 the base times the height. Okay, so for any of these triangles, its area is going to be, we could call either of these can be the base. We could call this the base and this the height. And so we have 1/2 A times B. So the area of one of those triangles, 1/2 A times B. The area of 4 of those would be 4 times 1/2 AB, or 2 AB. Okay, so this 2AB is going to be the area of all those 4 triangles. If you notice, if you think about it, we had a 2AB back in that other expression that we had. Okay, so let's summarize what we have now. Okay, so this is what we know now. We know the area of that large square with side lengths a plus b is a squared plus 2ab plus b squared. And this will work for any a or b. That's what's nice about doing a proof like this. We're not just showing it for one triangle, we're showing it for any triangle. The area of the 4 triangles around the perimeter of that square is 4 times the area of one of them, because they're congruent triangles, so they all have the same area, is 2AB, or 2A times B. Okay, so what we need to do now is go back and look at that diagram again, and we need to make sure that the what looks like a square in the middle is actually a square. because we know that these are right triangles, because that's what we started with. So we know that this is a square, but we don't necessarily know that these are 90-degree angles yet. So let's look at it. What do we know about the angles in these triangles? Well, we said, that and I'm going to label these. In this right triangle, if there's one 90-degree angle here in the corner, that the other two, so this is my 90-degree angle, that the sum of these other two angles must be 90 degrees because the entire triangle is 180. So I know that those two add up to 180 degrees. So let's look at this diagram again. We're going to label it. I'm going to use colors though, because I think it will make it more clear. So if I look specifically at this angle here, and I'm going to find that angle on these other triangles. So I want it to be a corresponding angle. And so it's the one, so I can kind of look at these side lengths where A and C meet is this, we're going to label with the blue. Okay, so it's where the sides A and C meet. So it's over here in this one where A and C meet, and it's here in that one. Okay, and then this other angle that we're going to label in red is right here. It's where B and C meet, right here, where B and C meet. So I can see I've got another one right here, one up here, and one over here. So where B and C meet, I'm going to label with my red. Okay, so let's take a look at one of those where let's look at this side length. Okay, so this is a straight angle along here. So the three angles on it going all the way should add up to 180. So what I know is that a red plus a blue equals 90. So what does that leave for these angles here in the middle? So if this one, the red and the blue, add up to 90, then this angle here must also be 90. So that's a 90-degree angle. That's a 90-degree angle. So is that one, and so is that one. All right, and if those are 90, then this is going to add up to 180 on all these straight angles right here. So that's pretty cool. So now I've proven that this is a square. This is indeed a square here in the middle. And what would its area be? Well, its area would be base times height or length times width, whatever you say, but its area is going to be c squared right there. Okay, so we're going to go back and look at that equation, and we're going to straighten this out. So that is c squared in the middle. Okay, so now we can go back to these notes here, and we know that the area of the four triangles is 2AB, and we know something else now. We know that the area of the center square, the smaller one in the center, and we know that it's a square now because we proved that, is equal to c times c, or c squared. All right, so we're going to put this together in one equation, because the area of the four triangles, this whole bit right here, all of this together is equal to the area of the large square. So I can write one equation with all of this in it. So let's do that now. Okay, so what do we have? We have the area of I'm going to write it in words first. The area of the large square is equal to the area of the four triangles plus the area of the center square. Okay, so sometimes it's helpful when you're going to write an equation to write the parts out in words first and then substitute what you know. Okay, so what do we know about the area of the large square? Well, we did the math on that, and we know that it is a squared plus 2ab plus b squared. Okay, so that is equal to the area of the four triangles, which we used 1/2 base times height, multiplied it by 4, and got 2ab for that, plus the area of the center square, which was c squared. Okay, so you might see this popping out now, but notice that we have this quantity of 2ab on both sides of this equation. And so we can subtract that off using properties of equality and what you've hopefully learned about solving equations. I can subtract 2ab from both sides of this equation, and the equality will still hold. Okay, so when I do that, I'm left with only a squared plus b squared on this side of the equal sign, because this 2ab minus 2ab becomes 0. Same thing over here. This becomes 0. And we're left with only c squared on that side of the equation. So this is, right here, the Pythagorean theorem. And that's what we set out to prove. Now, this was a pretty clever idea to draw that square within a square. Oh, I can't even draw it. Let's see. Go here, and here, and here. To draw this square within a square was a pretty, oh, that's not good. That you remember what it was. Pretty clever idea that I didn't come up with, but somebody else did. But we worked through it using what you know about geometry, what you know about solving equations, and we were able to prove that this will be true for any right triangle. So let's do some examples now with actual numbers in them, and we'll show you how this works out, how we can apply the Pythagorean theorem. So you can turn to your classwork pages now, and let's look at example 1. So now that we know what the Pythagorean theorem is, we're going to practice using it to find the length of a hypotenuse of a right triangle. So remember that the hypotenuse is always the one opposite the right angle. So if you find the right angle, draw an arrow across the triangle, that's going to be your hypotenuse. So in this particular example, we know the sides, we know the lengths of the legs, and we're asked to find the length of the hypotenuse. So we're going to use the Pythagorean theorem here. A squared plus b squared equals c squared. That's right here on your page. And we can just fill in the numbers that we do know. Okay, so this example has been worked out for us. So we've plugged in, let me get my pen back. We've plugged in a equals 6, b equals 8, and c is the one we don't know. So we end up with this equation when we put that in the Pythagorean theorem. 6 squared plus 8 squared is c squared. 6 squared is 36. 8 squared is 64, which adds up to 100. So we know that c times c equals 100. Well, we can figure out from that c is equal to 10, because 10 times 10 is 100. All right, so this length here is 10. Okay, a double check on that. Remember we said the hypotenuse is always going to be the longest leg because the 90-degree angle is the biggest angle in that triangle. So if we end up with a number that's not bigger than 6 or 8, then we know we've done something wrong. But so for this one, it checks out. That's the longest leg of the triangle, and it's 10. Okay, let's look at the next exercise. Okay, so in example 2, we're being asked to find the length of the hypotenuse of the right triangle. We know that a squared plus b squared equals c squared. We'll let this one be a, and it doesn't matter, right, which one is a or b, because I'm just going to be adding them together. This can be our b, and c is the hypotenuse. So a squared, if we put in 3 for a, 3 squared plus 7 squared is equal to the hypotenuse squared. 3 squared is 9. 7 squared is 49. And that is c squared. So 9 plus 49 would be 58 is equal to c squared. All right, so we need to think of a number that we could multiply by itself to get 58. And for 58, there isn't a number that we can find that we could multiply. If we put in 7 times 7 would be 49. The next number up, 8 times 8 would be 64. So it's somewhere between 7 and 8, but we can't be sure. So in this lesson, we're going to say that if we can't find a perfect square like we did in the first example, if 58 is not a perfect square, so I can't know exactly what it is, we can just leave it at c squared equals 58. So you can leave your answers in this form. Some of you have learned square roots, so you could say something like c is equal to the square root of 58. If you have not learned that yet, don't worry about it. Leave your answer just like that. C squared is 58. I can't simplify that any further with the numbers that I know at this point. Okay, and you can check the solution key to see if you're on the right track with doing these, okay? All right, let's do another example. All right, after those two examples, you can go ahead and do exercises 1 through 5 using the same technique. Come back and we'll check them together and see how you're doing, and then you'll be ready for, we'll summarize what we've learned, and then you'll be ready for the exit ticket and the problem set. So, yeah, once again, pause the video, work on exercises 1 through 5. Okay, so for this first exercise, I've written the Pythagorean theorem, substituted for the legs of this triangle, A and B, 3 and 4. So 3 squared plus 4 squared equals c squared. 3 squared is 9, 4 squared is 16. That adds up to 25. So c squared equals 25. Now 25 is a perfect square, so I can know that c is equal to 5 in this case. It's a perfect square. I know that 5 times 5 is 25. So c, this side length, is equal to 5. This is a famous right triangle called a 3, 4, 5 triangle. It's used a lot in construction for getting angles of cabinets and concrete slabs or whatever square. I know that if I have a 3, a 4, and I make the hypotenuse 5, that this is going to be a right angle. So it's a 3, 4, 5 triangle, and those come up a lot. Okay, so let's look at number 2. Substituting into my Pythagorean theorem up here, a squared plus b squared is c squared. I'm going to get the equation 8 squared plus 11 squared is equal to c squared. So I've got 64 plus 11 squared is 121, and that is equal to c squared. So if I add those two together, I'm going to get 185 for c squared. And it is helpful to learn some of your perfect squares, but this is not one of them. So I'm going to just leave my answer as is. So I can leave it just here at c squared is 185. And again, if you are familiar with this, we do know that c is the square root of 185, but your answer key is going to have that, and that's all I'm expecting right now. Okay, let's do another one. This one was 9 squared plus 4 squared is equal to c squared. So I have 36 and 16, which would add up to 52. And, oh, wait a minute. No, it doesn't. 9 squared isn't 36. You're screaming at me, right? 9 squared is 81. Don't know what I was thinking. I was thinking 9 was a 6. So this is not 52, but this would be 97, right? 97 is c squared. 97 is not a perfect square, so we'll leave our answer just like that. Okay, let's do the last couple here. Okay, so for this one, my legs are 5 and 2, and here's my hypotenuse. So I know that 2 squared plus 5 squared is equal to c squared. And so that would be 4 plus 25. So this would be 29 is equal to c squared. 29 is not a perfect square, so I can leave my answer just like that. Let's look at the last one here. I get 1 squared. I've got a triangle with a 1 and a 9, plus 9 squared is c squared. So I've got 1 times 1, which is 1. 9 times 9, which is 81. So this gives me 82 is equal to c squared. Once again, not a perfect square, so I'm going to leave my answer in that form. Okay, let's summarize what we've learned. Okay, so we've learned some vocabulary that goes along with these right triangles. So I have this right triangle, ABC, here. C is the vertex of the right angle. The sides AB, or AC and BC are legs. So this is a leg, this is a leg. And side C, which is opposite the right angle, is called the hypotenuse of triangle ABC. Okay, and we talked about how we're calling side A is opposite angle A. Side B is opposite angle B, like so. And the Pythagorean theorem tells us that for any right triangle, remember this only works with right triangles, we know that the sum of the square of the legs is equal to the square of the hypotenuse, or a squared plus b squared is equal to c squared. All right, so you can do your exit ticket and problem set now. This should be fairly straightforward for you. And we will be back with lesson 16.